We have a severe problem with generative video. The current crop of autoregressive models can output stunning short clips, but if you command them to generate an environment indefinitely, the output inevitably collapses into smeared, chaotic noise. To build an interactive world simulator, a model must adhere to a strict rule of causality. We define this with a causal factorization equation. The current state, x sub t, depends entirely on two specific parameters: past visual states and current action inputs. Generating 3 seconds of video is easy. Forcing a model to respect this causal equation over thousands of frames in real time requires processing mathematics at a scale standard prompt-to-video architectures simply cannot handle. This is the engineering problem targeted by LingBot-World-Infinity, a 14 billion parameter open causal world model developed by Robbyant. The Robbyant research team engineered this system to neutralize the two primary bottlenecks of interactive simulation: long horizon drift, where the visuals degrade over time, and interactive latency, where the model fails to respond instantly to user inputs. They approached these bottlenecks with a two-part solution. To fix the drift, they rewrote the attention mask at the matrix level. To fix the latency, they wrapped the model in a dual-agent harness. By separating the macroscopic semantic logic of the world from the microscopic engine that renders the pixels, they built a framework capable of truly infinite generation. In autoregressive video training, models use a standard lower triangular attention mask, where new frames attend to past context. As the sequence lengthens, this context window grows overwhelmingly dense. The model leans entirely on this history, causing overfitting and visual degradation. To fix this, the team engineered the MoBA mask. They appended a bidirectional, full attention block directly to the standard teacher-forcing mask. Zooming into the self-attention split, you can see the autoregressive steps clearly separated from this new bidirectional block. That bidirectional block acts as a mathematical regularizer during training. It prevents the model from collapsing under its own context weight, allowing for flexible length generation. The self-attention handles the frames, but the cross-attention mask determines how the model processes user prompts. This cross-attention matrix maps the routing. Autoregressive rows are strictly restricted, attending only to a background prompt and the specific text prompt for the current chunk. This restriction acts as a hard physical boundary, ensuring future semantics cannot leak backward into the causal chain. By contrast, the bidirectional rows expand outward, connecting to a single overarching global prompt that anchors the scene's broad context. This dual mask design forces the model to respect causality at the token level, generating new states indefinitely without being suffocated by its own historical outputs. A 14 billion parameter model rendering frames step by step is too slow for real-time interaction. The massive teacher model must be compressed into a fast, few-step student model. This flow matching graph represents distribution matching distillation, tracking a probability trajectory from a noised student to a target. Standard setups force the student to minimize the difference between its predictions and perfect teacher-forced states. But if trained only on perfect states, a model never learns to recover from its own mistakes, compounding the visual drift. To fix this, researchers bypassed static teacher states entirely, executing the distillation over long, self-rollout trajectories. The student model is forced to observe the consequences of its own outputs. It optimizes against the exact state distribution that its own predictions induce. Exposed to its own noisy rollouts during training, the student develops a self-correcting mechanism. It learns to actively neutralize visual drift before it accumulates. An autoregressive video model can only survive infinite generation if its training data explicitly includes its own predictive errors. Even with drift eliminated, a raw frame predictor is not an interactive simulator. It doesn't understand rules, causal logic, or discrete objects. To fix this, the team built a director-pilot co-simulation framework. The director, a vision language model, governs semantic rules and issues structured event cards. The pilot, the diffusion transformer, receives these cards, handling physical dynamics and strictly rendering the final pixel transitions. This harness operates in two distinct interaction modes. In direct semantic interaction, the VLM reads the global frame and injects high-level environmental events directly without requiring manual object masking. For localized actions, tracking-assisted object interaction uses a segment anything model proposal loop. It identifies specific objects in the frame and tracks them across chunks, allowing the user to trigger a targeted action. Manual user inputs, like WASD movement or camera poses injected as Pluker embeddings, bypass the semantic engine entirely, feeding directly into the physical state. The execution timing is exact. When a user issues a command, the input queues up and lands exactly at the next chunk boundary. Actions register to a persistent state ledger. Inputting a forward command drives the camera longitudinally across every chunk until you explicitly send an idle command. By delegating high-level logic to the director and pixel generation to the pilot, the architecture solves interaction latency while preserving strict narrative coherence over time. That is the mathematical theory. Now we have to look at what this architecture produces in a live deployment scenario. Consider a first-person simulation of a bamboo canal. The user navigates the physical space using low-level WASD controls while registering semantic commands to numeric hotkeys in the interaction ledger. Thanks to the MoBA Attention mask and self-rollout distillation, the architecture maintains the structural integrity of this environment over an uninterrupted hour-long session without degrading into noise. If the user presses a hotkey to summon a snowstorm, the VLM director intercepts that global state shift, computes the logical constraints, and passes the updated parameters to the pilot, which seamlessly renders the weather change in the next chunk. However, we have to separate the theoretical maximums of the hosted model from the hardware constraints of the current open-source release. The research team lists a headline capability of 720p video running at 60 frames per second, but that performance relies on an unreleased external deployment stack. This pipeline requires a spatio-temporal refiner to take the raw output, upsample it, and synthesize intermediate frames using compiled TensorRT engines. The publicly released reference script processes causal inference chunk by chunk using KV caching. It tops out at a 480 by 832 resolution and requires an 8 GPU cluster to run. Even with high hardware demands, a localized interactive world model enables immediate game-level prototyping and provides an engine for generating massive amounts of synthetic data for embodied robotics, all without authoring a traditional 3D scene. Infinite world simulation cannot be achieved by merely scaling up prompt-to-video generators. It requires direct architectural interventions against mathematical drift and a strict systems-level division of labor to manage causal reasoning.